I'm Donald Tarter of the Sociology Department at the University of Alabama in Huntsville, and this is the last in our current series of interviews with the fathers of rocketry. As you know, this series has been entitled Our Future in Space, Messages from the Beginning. And today we have as our guest an individual who is going to primarily focus upon the future. Although the title, The Future, has been in our project, you will probably know, if you've watched the entire group of tapes, that we have really focused on the past. But we have with us today a gentleman that is keenly involved in working out plans for our future in space. Our guest today is Dr. Georg von Tiesenhausen. He likes to be called George. He does not like to be called Doctor. And although we have been very formal in these past tapes, today we're going to try to be a little bit more informal, so I'm going to refer to Dr. von Tiesenhausen as George and Mr. Dannenberg as Conrad. As usual, Mr. Dannenberg is our co-host here, and as usual, I am going to let Mr. Dannenberg begin the questions.
Thank you, Don. George, although we want to concentrate on the future today, of course we still want to go back in years, a number of years, and start with the initial activities in Peenemünde. Can you tell us briefly when you came to Peenemünde, what brought you there, and what were your first assignments at that time?
To enter the area of Peenemünde was one of the greatest surprises in my life, because since the age of 14, I knew exactly what I wanted to do with the rest of my life, and that is to be involved in rocketry and spaceflight. So in 1943, in the middle of World War II, I was transferred to Peenemünde, and I was standing in awe of what I saw there. Whoever has had a chance to see pictures of Peenemünde will understand that. I had great ambitions, finally to build rockets. My first job was to design a bolt, and my boss told me if I do a good job, I may design the nut to go with it. But then I got heavily involved in the design of test facilities, test stands, for rocket engine as well as for complete rockets. You may not think it's possible, but in those days, we already planned to go to the moon. We had one test stand for 200 tons of thrust built. Of course, nobody knew what it was all about. We had people in the corner designing moon rockets secretly. However, we were involved in designing and building weapon systems, as you well know, the V2 and also the V1. I was involved in both areas, in the ground support equipment and in test stands. The end of the war, of course, put an end to these activities. Several years later, I was fortunate to be invited to the United States, and we continued our activities in weapon systems, ironically. Again, we tried to go into space. So in one corner were a few people who designed satellites that we hoped to launch eventually. And that's what happened. Until finally NASA arrived, and we were legitimately in the business of going into space. So history repeated itself in Peenemünde and in the early days here in the United States. The interesting thing was that the rocket team, when it came to the United States and established itself in Huntsville in 1950, had about the same organization than we had in Peenemünde. That organization was so efficient that it was completely maintained until about 1970, the year Werner von Braun left the Marshall Space Flight Center, going to Washington. That coincided, of course, with the time where we had essentially finished our Apollo work. under Dr. von Braun, and where we started to diversify into a multitude of different projects. But the early days of Peenemünde laid the groundstone, the cornerstone, to what we were doing here. Our first missile here, the Redstone, was just a glorified V2. It ran on alcohol and liquid oxygen, just like the V2. It was just bigger. And the rest of the rockets we built, Pershing, Jupiter, and so on, essentially were just extended and further developed V2s. The principle throughout all these rockets was exactly the same. And the first departure, of course, came about when we started working on the space shuttle. But even that wasn't new. The space shuttle concept was already proposed in the 30s, in many ways. But we started really implementing the space shuttle concept. So Peenemünde and the people working there were really the originators of most of the concepts that we deal with today. And that is a very interesting historical fact, I think.
Let me ask you a few questions relating to Peenemünde. You said you came to Peenemünde in 1943.
Right.
I seem to recall you were a member of the VKN, Versuchskommando Nord.
Yes.
You came there as a soldier.
Yeah. And we wore uniform during the whole time in Peenemünde because we were under military authority there. And so, however, we had the chance to select either a military wage or a civilian wage. So I selected the civilian wage because it was higher, simply. But we had that choice. The interesting thing in Peenemünde was that a boss sometimes was a GI, while the people working for him were lieutenants or other higher ranks. And surprisingly, this worked quite well. While outside the business hours, the relationship, of course, was reversed again. So, but that worked quite smoothly and quite well.
What was your rank in the military?
I was
one of the higher-ups?
No, I was a sergeant. That's as far as I made it. But we were surrounded by lieutenants and captains and colonels, and it really didn't make any difference during the working hours.
George, from your earliest days, you seem to be right out on the leading edge of projects. At Peenemünde, and incidentally, I forgot in my introduction to identify George as the assistant to the director of the Office of Advanced Systems at NASA. He is still actively engaged in the program, being the last of the German team to be there at NASA. And he's still very actively engaged in technologies that are at the leading edge of space activities today. But back in 43 and 44, you were also at the leading edge of technologies at that time. One little-known fact of history concerns the project Proofstand 12. Could you describe that just a little bit and tell us what it's about?
Proofstand 12, that means test stand number 12, was a code name for a project that was so secret that even my next colleagues were not supposed to know about it. We wanted to give the V2 a longer range, say, launch a V2 into Manhattan, or not one, but as many as possible. So what we laid out was a submarine-launched V2, and the setup was as follows. There was a mother submarine towing number 5, 6, or 7 daughter submarines. These daughter submarines were hollow cans, each one containing a V2. In the area of the destination, these daughter submarines would detach from the mother submarine and fill their ballast tanks and erect vertically in the water. so the tip of the can would look above the surface. Then an opening, a hatch would open, like two halves, and the V2 would be launched out of this can from a distance of, say, 50 miles offshore, or 20 miles. We managed to get as far as having a mock-up built, having some metal bent at the shipyard for the cans, and did some test firings out of these cans. The end of the war put an end to this effort too. I still have some documents about it, and some American documents contain some mention of this, but very little. This is a very little known Peenemünde activity.
What would have been the launch activity? Would people have been on the Tarter submarines to help in the preparation of the V2?
Yeah, there would be.
Because we normally needed quite a crew in order to do this launch activity.
Automation was not too far advanced in those days, of course, so before the launch, a crew would go over into these cans and transfer the oxygen, the liquid oxygen, which was in an insulated tank separate from the missile, into the missile tanks. The other missile tank contained already the alcohol, which was the fuel. So after the transfer and after a last checkout, then these crews would return to the mother submarine, and the launch could begin.
They probably also had to put the hydrogen peroxide into
all these
catalysts in order to decompose it.
Yeah.
And of course the guidance system had to be
turned on and aligned and so on. That was quite an operation. We worked with five project people on this project. Our leader was Mr. Tessmann, and Bernie Tessmann, Hans Hüder, the late Hans Hüder, Dr. Hans Hüder, Hermann Hofen, who lives in Germany now, and I forgot the others, I think, and myself, and then I think it was one more.
At this particular time, of course, this was a missile concept that would have been launched from or at the surface of the sea, but could you envision at all the Poseidon type beneath the sea launch at that time?
As a matter of fact, we did an underwater launch of a rocket. Dr. von Braun was quite familiar with a submarine commander who visited one time at Peenemünde. And Dr. von Braun talked him into staying for about 5 days. And he agreed, and while they were together, a crew went on the submarine and welded on a launch platform outside on the submarine from which you could launch solid rockets. They were mounted and installed. Then the submarine went offshore and dove about 50 feet or so. And those rockets were then ignited from underwater and made their ballistic trajectory. That was the first time in history that a rocket was launched from underwater.
Fascinating.
After at the fourth day, the crew went back to the submarine, cut off the platform, ground everything smoothly, painted it over, and there was not a trace left from what had been done, because this was done without authorization by the Navy or anybody else. So we were pretty freewheeling in those days. The main thing what counted was results, of course.
I have two more questions concerning Peenemünde. Before you came to Peenemünde, before you were transferred, did you know about it? Did you know what was going on, or was it a kind of a surprise by the time you arrived there?
The secrecy of Peenemünde was so tight, I did not have any idea what was going on. The reason I came to Peenemünde was the result of an examination I had to undergo at the German Air Force Command in Berlin. And they looked at my credential, and I happened to be good in two areas. One was thermodynamics, and the other was design. So they took a big stamp, stamped the document, and said Peenemünde. which was for me like a Chinese word. And I took this piece of paper, got on the train, and when I entered Peenemünde, I had no idea what I was about to enter into.
So it was a real surprise that you apparently knew about rocketry. You mentioned it earlier.
Yes.
You probably had read Overt's book. Many people had in those days.
And the movie that turned me was Frau im Mond, Woman on the Moon, by Fritz Lang, an UFA movie, which turned me around at the age of 14. And entering Peenemünde was the fulfillment of that dream.
Now, when you came to Peenemünde, even the first successful V2 had been launched already.
Yeah.
You apparently had not heard about this launch.
No,
because you said earlier you didn't know anything about Peenemünde. But when you finally came there, and apparently you got even some advanced assignments, did you foresee what would eventually come out of this? Or is the present development also a surprise to you?
No, very definitely. I saw space flight. In every rocket from the V2 on, I saw space flight coming. There was no doubt in my mind whatsoever.
Particularly after having read Overt's book, that of course really puts you on the track.
Very definitely. Overt's book, Into the Planetary Space, was read by just about everybody of us, I think. And so there was no doubt that we would go into space, not the slightest doubt. And of course, as I said before, we planned already a multi-stage moon rocket, which we put on the drawing board secretly in those days. Of course, the discovery of that would have meant prison for everybody involved, because we were supposed to do weapon systems. So we are all geared to spaceflight, not the slightest doubt. And you have seen, we all came over here, and that's what we're trying to do.
You came here to America in 1953.
Yes.
Were you at that time hoping to enter directly into the space field, or did you know that you would be involved in military activities for a while?
I knew I would be involved in military activities, but I was before. But the hope was still there. This is just a prelude to spaceflight. The development of the technologies necessary, the combustion, the engines, the guidance systems, all that was needed for spaceflight. So history repeated itself. Again, here we started off building weapon systems, the Redstone, the Jupiter, the Pershing, and so on. And history repeated itself again, that in some corners, some of us were busy designing satellites, scientific satellites. And again, they were checked upon. Our Department of Defense, Secretary Wilson, he sent people around to check if we were building satellites. Of course, they didn't find any. Of course, we were building them. So when the time came and the Russians beat us, we had a few satellites which we had to dust off and finish, and could launch Explorer 1 as early as possible, within 90 days from the go-ahead. So you see the parallel again to Peenemünde. We always wanted to go into space, but the technology was developed for weapon systems.
But you went with NASA immediately upon its formation.
Immediately, there was not the slightest doubt. NASA opened for us the door into space. Now we could openly say, all right, we're building space vehicles, we're building satellites. We want to go to space, we want to go to the moon. So we all moved to Huntsville in the early 50s, and around 50, I came 53. A little place in North Alabama where everybody from Tennessee was a foreigner, even. So we came in. People thought we were crazy. And then we were talking funny, and then they learned we wanted to go to the moon. then they knew we were crazy.
Were you surprised, or was a lunar excursion in a way something you really had expected at that time?
No, I did not. I would have expected that we first invade, so to speak, Earth orbital space, that we build a space station, that we build an Earth orbital capability, something that we are doing now, before we go to the moon, as a basis. So we have a basis to assemble lunar vehicles from there to go to the moon. Of course, as you know, the direct flight to the moon was a rather political decision. But nevertheless, one of the major challenges in history of technology. It is indescribable, the problems that had to be overcome to launch a manned vehicle to the moon, land there, and return people safely. That is an unimaginable feat, still today. As you know, nobody else has attempted it ever since. And so, now only we go back to Earth orbital space. And as you know, we are preparing a space station to be in position in the early 90s. So, in my opinion, we sort of did things backwards. But it's okay. The Apollo program has developed a lot of technology that is useful right now, in spite of the fact that it was a dead end. Where are the Saturn vehicles now? They are museums, if they still exist. So we had all the rights in the world to go now to vehicles that can be reused over and over again, as you know, the shuttle is, which is a logical thing to do. The time of expendable rockets was over, definitely. So the evolution toward the shuttle was quite logical. There was no other way. And as I said again, even the shuttle was not a new idea. It was originated in the 30s by various promoters for spaceflight, Sanger and others. So that's what we are doing now.
I know, George, that you were involved quite a bit in early space station plans, early space station designs. What NASA is doing right now, is that pretty much what you had expected? Or would you rather have seen, for example, a much bigger space station than what the present plans are?
Yes, I would have. Now, it is so in the technology that the space station has to adapt to what kind of launch vehicles we have. The Saturn V had a 30-foot diameter. So anything where we would build a space station from could have that size. Now, the shuttle orbiter has only half that size, 15 feet. Nothing can be over 15 feet in diameter. So that affects the picture of what we are going to get from the space station. So the space station will consist now of relatively small parts, modules, not larger than a little bit less than 15 feet. While our early space station work was based on these large modules carried aloft by the Saturn V. As a matter of fact, we have a number of concepts of large space stations. One was called a space base. A space base was to house 100 people. Initially 20, then 50, then finally 100 people in space, with a huge nuclear power plant to supply all the power for this, because solar arrays would have been just astronomically large. So we did indeed study space stations since always, actually ever since. There was always somewhere an effort going on to design space stations. We really seriously went about it in around 1970. And then, of course, the shuttle development took precedence. It was an either-or. Either shuttle or a space station. Of course, our question was, if you have a shuttle, it has to have a place to fly to, which is sort of a space station. On the other hand, the politician said, if we have a space station, then we have a good argument of having also a shuttle, since the fund was only sufficient for one of each. It was decided to build a shuttle. Now we have a shuttle, and the space station, as you know, is going to follow in 8 or so years from now, 7, 8 years.
On the other hand, of course, we had a space station in the form of Skylab.
Yeah.
Were you involved in the early Skylab designs?
Yeah. The Skylab.
And why did we not decide to keep Skylab going with just a few minor technical additions? We probably could have built it in such a way that it would have been and would still be today the first space station. The
Skylab was a most interesting example on how Dr. von Braun went about new projects. As you may know, the Skylab was housed in the structure of an upper stage of the Saturn, the so-called S4B stage. And we were promoting a space station using this empty stage after it had been used up in space to fit it out with equipment inside and have a space station. It was called the wet space station because it carried hydrogen before to get up into space. Then when the hydrogen would be gone, the inner volume would be ventilated and equipped. Everybody thought this was the greatest idea in the world, and the project was approved. Later we found out it wasn't that easy, because see, where the money goes in the space station is not in the hull, in the structure. It's what is inside the space station. So more and more aids and equipments were added to the space station. And finally, it became such a concept that you could not do it in space anymore. You had to outfit it on the ground. And that's what happened, as you know.
That was in the dry workshop.
That was turned out to be the dry workshop, because it was never wet before. So we fitted out a complete space station on the ground with all the equipment and instrumentation and life support inside already. And then put it on the Saturn and launched it into space. And that is where our first experience was made by 3 astronauts at a time, 3 times, to be in space for long periods of time. They did their scientific experiments. They learned how to work in space. They learned how to repair their own space station, which was damaged at one launch. So a multitude of valuable experience was gained. Now, the cost of the space station set a limit to what could be done. Of course, from the wet workshop to the dry workshop was a cost increase, naturally. So a lot of things were left off. For instance, how to refill the empty tanks for life support, oxygen. How to refill the propulsion systems. How to extend the life of it beyond a certain limit. That wasn't there. Another accident happened that the sun acted up. The sun acted up in emanating much more so-called solar wind than expected. And the effect of the solar wind in the early 70s was that and the mid-70s was that the Skylab orbit decayed rapidly, because the drag was increased much more than we expected. What did we expect? We expected to have the shuttle ready to rendezvous with the Skylab and give it another shot by having a specially built propulsion system attached to it. Two areas worked against us. One, the higher drag, which decayed the Skylab orbit rapidly. Secondly, the extended development time of the orbiter. The orbiter was a tough job, as you remember. It took many more years. So the orbiter wasn't ready. The orbiter wasn't ready, and the Skylab was about to give up, which it then did.
Right.
As you remember, it came down mostly over Australia
In 79.
in 79, and it created quite some excitement. So two things worked against extending the Skylab time: the rapid decay and the long development time of the shuttle.
George, there's quite a bit of talk now. Just this last Sunday in our local newspaper, there was a large article about a mission to Mars. And really, before we got to the moon, you were engaged in a project that was designed to try to get to Mars by 1982. Could you give us a little insight on that project?
Yes, of course. During the lunar work, we already thought about Mars. In front of everybody else, the late Werner von Braun was a pioneer in designing Mars missions and promoting them. So naturally, a part of us were involved to lay out Mars missions during the 70s. Our work took place during the 70s. And we had some goals to start a Mars mission, actually mission in 82 and in 84. Now, the way we went about those times, was we had nuclear propulsion. The launch vehicles to Mars were filled with hydrogen, no oxygen. We didn't have any combustion. So what heats that oxygen? That oxygen was heated by running through a nuclear reactor, coming out the other end through a nozzle and propel the stage. So that was under development. Nuclear propulsion was under development in the Mojave Desert. We had several reactors running that way at that time. So the other people then looked at the launch vehicle and at the spacecraft. We would go to Mars, which would take about a year of flight time, with two vehicles. If something happened to one, the crew always could get over and get into the other one. So two vehicles would fly together to Mars over a period of 1 year. Arriving at Mars, they would go into a Mars orbit. And out of the vehicle would come a Mars lander. Similar, then out of the Saturn came a vehicle to land on the moon, the lunar lander. So Mars lander would then descend to the Mars surface on a pre-selected site. And stay there for 60 days and do research. Then out of the lander, the central piece would be launched again back into Mars orbit, similar to the lunar mission, where the upper part was then launched again into the lunar orbit. So the central part would then re-rendezvous with the waiting spacecraft in orbit, dock to it, and then would return to Earth again. So that was, in a nutshell, how we planned the Mars mission. Now, we're planning again the Mars mission. The interesting thing is we planned it entirely different. Entirely different. We have learned a lot. We seem to have been very naive in those days when we planned the first Mars mission. And technology has advanced in a number of areas that will change our approach to Mars missions. First, the wide consensus is that we should go to the moon first. The moon is an excellent training ground, a demonstration ground for a Mars mission. You can try out all your equipment there in relative safety. You're only 3 days away from Earth, rather than a year. So we would learn and develop our technology for a Mars mission using the moon, which has similar temperature differences, not quite the same. Of course, it has no atmosphere, but the atmosphere of Mars isn't much to speak of either. It looks that we will first attempt to establish a base, a permanent base on the lunar surface, and then develop the technology for the Mars mission.
Would we still use nuclear propulsion?
Yes, but different nuclear propulsion. The propulsion people tell me that the preferred way is nuclear electric. With other words, you generate electric ion propulsion by using the energy of a nuclear reactor. And that is more reliable and has less drawbacks than the brute force approach we had 15 years ago. The propulsion so will be nuclear based, but in a different manner. Again, more than one vehicle is planned. And again, an interesting difference. One of the future major developments in spaceflight will be automation, robotics, and machine intelligence. The exploration of the planets already, the outer planets, is done by robots, as you know, unmanned machines, who are still pretty dumb. But in the next 10, 15 years, we will have smart machines that explore the planets. One reason for that is the long delay time for giving signals to those machines from Earth, which takes many hours. And a lot of things can happen in several hours. So the machines have to be self-sufficient. So the role of automation will play a major role in Mars exploration. And I foresee that even on the Moon, we may have an automated robotic depot established first. For example, on the Moon we can deposit an automated, fully automated oxygen factory. The lunar surface material consists of about 45% in average of oxygen. Unfortunately, it is tightly bound to other elements. So you have to free it, but it's there. People have already worked out processes to do that here on Earth. So the automated processes would work and establish, say, an oxygen depot, which would be invaluable for manned landers, for breathing, of course, and even for propulsion. Secondly, the lunar surface lent itself excellently to produce solar cells. There's silicon, there's glass, there's aluminum, most parts you want. With other words, you can generate power. So an automated solar array factory. So automation will play a role in establishing certain deposits, certain areas on the Moon that have already certain supplies. And the same will happen on Mars. And the way I personally envision it, a Mars mission has to be safe. So there will be depots established in Mars orbit with food, water, oxygen, power to recharge batteries, whatever. So when they make it up to the orbit of Mars, they have a depot there. Secondly, a depot on the Mars surface for the lander. Again, food, water, oxygen, other supplies, spare parts, whatever. So these depots will play an important role. Some of my colleagues have gone beyond that. They have discovered certain stable orbits between Earth and Mars, along which they want to have depots established. So whenever during the trajectory between Earth and Mars something happens, they can dock to the next depot and rendezvous with it on the way already. So that has been studied a number of ways and a number of times.
George, with all this elaborate preparation, the depot concept and getting to Mars and so forth, wouldn't it be a shame to get a crew there and then have to come home in a few months or a year or so after? Is there any consideration being done for leaving a permanent colony of human beings on the surface being periodically supplied?
Yeah. You touch on the question that interests me very much. That is how humans in particular and in general going to react to these undertakings. A Mars mission lasting 2 years may be still manageable, I think. People have been a year or so in Antarctica, cut off from everything, on submarines for many months. And we study those people and how their reactions are, their behavior, and try to extract information on what kind of people you put together in the first place for an undertaking like that. It's obvious that you cannot take just anybody and put them in a can and let them be together for 2 years. That just doesn't work. People are not built that way. So you would have to establish some compatibilities, of course. People who can indeed stay together a year or two. And that is being done with submarine crews and in Antarctica. And even prisons have been studied. So you as a sociologist, of course, are well aware of these problems. We, not being sociologists, have to be aware of it. And we make every effort to be. So we have done a lot of studying. Even on short flights, say a week on the shuttle, we emphasize the compatibility of the crew members. And this has worked quite well. And the criteria for compatibility have to be pretty strict because you are in a tension-filled environment. It's not a relaxing environment, like in a summer resort, where you can get along with just about anybody. But it is you are in a hostile environment, and you are in a tension-filled situation. So NASA has established criteria for that and has been doing pretty good so far. But I said 2 years may be a breaking point where you have to have a new approach. Say, if we go any further, travel times, manned travel times, will be much longer, of course. Then the question comes, is there a limit where we want to send people in the first place? And machines taking over permanently? Or can we extend the human characteristics required to stay together for, say, 4 or 5 years, 6 years? Is that possible? The answer to that is we don't know. We have not the foggiest idea. At the moment, the outlook is such that Mars is about the farthest planet where man will go. We have studies and plans for other planets strictly for robots, machines, intelligent machines.
That gets us into a marvelous area of discussion. I know you said your own career was launched by the movie Woman in the Moon, Fritz Lang's movie Woman in the Moon. A good number of people that are working in the space program today, I suppose, were highly motivated by Arthur C. Clarke's 2001. And Arthur C. Clarke's sequel to that movie, 2010, was primarily inspired by some work that you were doing. How replicating itself out there in orbit. You've done a good number of studies on self-replicating machines. Could you explain this concept to us?
That was one of the most interesting projects I ever had in my whole life. During the 40s and 50s, Dr. von Neumann, an Hungarian scientist, wrote a book, or started to write it, about the possibility that machines can self-reproduce. Unfortunately, he died before he finished the book. But he came about with 5 different ways how that would be possible. Other authors in his field The past NASA administrator, Dr. Frosch, was approached by Dr. Colombo from Italy to look into these self-replicating systems that von Neumann had postulated. And as most of this type of things, they ended up on my desk. And I was asked to comment on it. That gave me the motivation for study. I studied von Neumann and others. They explained the self-replicating capacity of machines in highly symbolic and theoretical language, which was mostly incomprehensible to me. And then as an engineer, I said there ought to be a way to bring this close to the engineering community. Fortunately, at that time, there was a workshop in Santa Clara University where this was one of the subjects. In my homework before and there, I tried to design a self-replicating system, the engineering elements of it, and tried to determine what each element needs to do so it can reproduce. And that came out very well. If I may say so, it was a fascinating environment at the university, very stimulating colleagues, and everything came together. We had several panels here, and only one panel on this project. We were looked down upon by the other panels. We were only 3 people working on this project, while the other panels had about 10 or 12. And as time went on through the 10 weeks, we became the center of attention. Our panel was what we came up with. It was fascinating. So we ended up with a project plan over 20 years to develop a set of machines that can self-replicate. We had to overcome a number of mental blocks. And one mental block, I have a collection of comments. One was that a machine that produces something is always more complex as a product, which is true, but it doesn't have to be. We overcame other problems, like people from the complained to us from the moralistic side. They said this was blasphemous to do it. Other people had contrary ideas and said, nature does it, why not machines? So that the opposite. And everything in between. So I was able to design a system that could self-reproduce. However, not only that, because you could rightfully ask, so what? What is it good for? These systems, of course, could also produce useful products after they finished replicating, which was the very idea. So what I came up with was a small lunar factory that you deposit on the lunar surface that self-replicates until you can turn it off when you have the proper capacity you want. I had to invent 2 things. First, a set of machines that can produce any product you want to. Of course, you have to feed it energy and material. But out comes any product you want to, upon instructions. My colleagues call this the Santa Claus machine. Yeah, that was established, that machine, it could be built on command with energy supply and information supply and material supply. It can produce any product. It was a universal product machine. A second machine had to be developed. That was the universal assembly machine. We call it the universal constructor. That is a machine with provision of power, of instructions, could assemble any machine from parts you want to. So these 2 were the core of the whole system. One that can make any parts you ask it to do, and one that can assemble these parts to any machine you want to do it. So that was published, and I published a second paper on how you control something like that. How do you manage something like that? Can it get out of hand? interesting questions had to be asked and answered. And so the approach taken there to manage and control the system was taken as being a parallel to how biological systems control their doings and operations and processes. That worked quite well. Arthur Clarke must have gotten hold of that report, and he, in his 2001 already and the 2010 book, if you have read it, he deals with a huge slab made of some strange material that follows these space explorers wherever they go. Naturally, it turns up again near Jupiter in 2010. And he uses the self-replicating processes for the slab to enter Jupiter and to convert Jupiter into a sun by transforming and first self-replicating the slab millions of times. And each one does its job on converting material that is on Jupiter. And that is how it ended his book.
George, after we have been to Mars and to Jupiter even just now, I would like to come back to Earth orbit again.
Yes.
I understand you are also working at the present time at a very interesting new project which will deploy from the shuttle a tethered system. Can you tell us a little bit more about this work on the tethered system and what you see as a future of systems of this kind?
Yes, I certainly will, Connie. A new element is at the present time being introduced into spaceflight. It's really not a new element. It's been first proposed about 100 years ago by the Russian Tsiolkovsky, but it was dormant. And we unearthed it, but it is new insofar as we apply it. And this new element is a cable, a long cable in space, say 50 kilometers long, 100, 150, 200 kilometers or more long. But what would one do with a cable in space? There are a number of things. Let me give you two examples. If this cable is a conductor, an insulated conductor, you deploy this cable from the space shuttle, say upward. How would it go upward? All by itself? Yes. What happens if you separate, you have a mass at the end of a cable, and if you separate that mass from the shuttle, a distance initially, then that upper mass has a little bit more centrifugal force, and the lower mass, the orbiter, feels a little bit more gravity. So these two forces keep on now separating the two masses, and the proof of that is that the cable between them is under tension all the time. Mm-hmm. There's a winch which lets go of the cable in a controlled way, so things don't get out of hand. So when you have deployed this conductor, say 20 kilometers or 50 or 100, then we have what amounts to an electric generator. You know the Earth has a magnetic field. The orbiter with that electric conductor move around through the magnetic field with orbital speed, cutting through the magnetic field lines. And as you know, that generates a voltage in the cable. So now we want not only a voltage, the voltage is about approximately 200 volts per kilometer of cable. Now we don't want only a voltage, we want a current. So what we do is we put on each end of the cable a sort of what we call a plasma contactor. One on top of the cable that attracts electrons that travel down the wire, and that's the current. And then on the orbiter, we have an electron gun that spits out the electrons again, and they circle back through the magnetic field back into where they came from. So we have a current flow. That's what we want. Now, so far, that is our theory. Is it going to work? So we have planned, and we have a project team right now that plans to do just that, to demonstrate this. We will have not a 100-kilometer conductor, but a 20-kilometer conductor, and hope to have some 4,000 volts generated, and maybe a half an ampere. We have quite a number of measuring instruments. It's not just to measure the electric energy that we collect, but also all the engineering areas that we have to investigate. How do we protect the orbiter from the high voltage, and what kind of switch gear do we need, and all this. So that is going to take place in late 87, 88, somewhere in that time frame.
George, we're coming down to our very last few minutes now, and this has been just an absolutely fascinating discussion, talking about self-replicating machines, etc. Human beings are self-replicators too, and we've done such a good job of self-replicating on this planet that we're beginning to get very crowded for space. You're one of the first people that I heard articulate the concept of Garden Earth and the future of space industrialization. As we close this discussion, could you give us your visions there just a bit?
Yeah, I think, Don, that is a comment that's close to my heart. We do overpopulate Earth. We do contaminate Earth with our waste of all sorts, including nuclear waste. We destroy our habitats, literally. And what can space offer for that? We already lay the groundwork in space for industrial involvement in space. In many industries, quite a number of industries are extremely interested and have invested in the precursors for space factories. Space is practically infinite, and there is no contamination problem. If we could have smokestacks in space, we would have them, and it wouldn't hurt anybody. But the irony is, space is a clean place, and we hope to keep it clean, but it is the ideal place for quite a number of industries. Metallurgical industries, biological, pharmaceutical industries, material, the basic industries, new materials. And these factories would be man-tended, ultimately, but automated, and return their products to Earth, thus supporting the motion that we move our factories out into space. There's plenty of space in space, and many processes prove to be much more efficient in space than on Earth. Besides, there's an infinite amount of energy available in space, which is not on Earth. You have a vast temperature range in space, from practically absolute zero to the temperature of the sun, if you concentrate it. You have a vacuum in space that costs a lot of money to generate on Earth. So the environment and the surroundings in space are ideal for future industry in space.
What a beautiful concept, George. As we close this series, now we are envisioning an Earth that is free from pollution, that has moved its industrial base to space. Yeah. And it's these gentlemen that we've been talking to in this series that initiated the processes that are making that goal possible. We do want to thank you, George.
Oh, you're welcome.
Conrad, I certainly want to thank you for this series of interviews that we've done. Hopefully we may be able to do a few more in the future, but for right now we're signing off with our Future in Space messages from the beginning. Thank you and goodbye.